This is lecture 14 in BBSP 610. We'll be discussing two sample t-tests. In the previous lecture, we discussed one sample t-tests, which you use when you want to test the null hypothesis that the mean of a given sample is equal to some specified value. And a two-sample t-test is when you want to test the null hypothesis the mean value in one group is the same as the mean value in a different group. In practice, you'll want to do this a lot more often than you will want to do a one-sample t-test. For example, examples of situations where you might want to use a two-sample t-test is, say you want to answer the question, do patients treated with the new drug have lower cholesterol than patients treated with the placebo? You would apply the drug, you would administer the active drug to one group, the placebo to one group, and then you would want to test the null hypothesis, the mean cholesterol levels in the two groups are the same. Or test the null hypothesis that mice treated with a growth hormone are heavier than mice treated with a placebo. Or, for example, you might want to test the null hypothesis that patients with metastatic breast cancer have different expression levels of a gene than patients whose cancer does not metastasize. So, quick review of t-tests. With the usual issue that when I convert these lectures from PowerPoint to Keynote, my X-bars all disappear. I apologize for that. You can use X-bar. The z-test is where you use X-bar for conclusions about mu, that if we know the value of sigma, then if we take X-bar, the sample mean, minus the hypothesized mean divided by sigma over the square root of n, that will have a normal distribution, mean 0 and standard deviation 1. And then, so do the hypothesis testing. You insert the hypothesized value of mu into this expression, calculate the sample mean, compute that test statistic. If it's too large or too small to be a normal 0, 1 random variable, then you conclude that, then you reject the null hypothesis, the mean is equal to mu 0. However, this only works if sigma is known. In the vast majority of cases, it will not be known. If sigma is unknown, then you can use a t-test, which is identical to what we saw in the previous slide, except instead of dividing by sigma over the square root of n, we divide by s over the square root of n, where s is the sample standard deviation calculated using the sample at hand. The advantage of this over the z-test is that it works even if sigma is unknown. Most of the time we won't know sigma, but if we don't know sigma, we can do a t-test and still get valid results. So now we'll consider the case where we have two samples that we want to compare, and the simplest case where we want to compare two samples is the matched pairs t-test. A matched pairs t-test typically will measure a variable of interest before and after a certain treatment is applied, or you may also, or sometimes you'll apply two different treatments to the same subject or similar subjects, and you take the difference between the two measurements for each subject and then test the null hypothesis that this difference is 0. It's exactly the same as the one sample t-test, only you're just testing the null hypothesis. These differences are equal to 0. The test statistic's the same. So an example of this comes from a former student in this class where she was measuring ATP production in mice. The ATP levels were measured in 12 mice. They were treated with some chemical that I have no idea what it is, and then the ATP measures were measured again 24 hours later. We want to test the null hypothesis that the ATP levels remained unchanged after treatment versus the alternative, they reduced the ATP levels. So I put this data set on the class Sakai site. It's called atp.csv, and it contains two columns showing the ATP levels pre-treatment, the ATP levels post-treatment. And each row is a given mouse. The left are the pre-treatment ATP levels, the right are the post-treatment ATP levels. And just eyeballing it, looks like in general the ATP levels are lower post-treatment. but we want to perform a rigorous test of that hypothesis. So the complicated way to do this, as we discussed earlier, you can actually compute the T-statistic using the formula from the previous slide. In this case, we're testing the null hypothesis that the mean is equal to 0, so x bar minus mu 0 would just be x bar minus 0, or x bar in the numerator. So we take the mean of this ATP.diff intermediate variable divided by the sample standard deviation divided by the square root of the sample size. That has 11 degrees of freedom because degrees of freedom is always one less than the sample size. And that's going to give us, and that's going to be a positive number, and PT is going to give us the left of that positive number. We want the area to the right of that positive number, so we take 1 minus this, then multiply by 2 because we want a two-tailed test. We end up with a p-value of 0.002, fairly strong evidence against the null hypothesis of no effect on the treatment. The easier way, as we've discussed before, is to use the t.test command. T.test ATP.diff, exactly the same as we discussed in the previous lecture. It gives us the confidence interval for the difference along with the p-value, which is the same as I computed on the previous slide. And if you recall from the previous lecture, if we call t.test without any parameters, then by default it will do a two-sided t-test, test the null hypothesis that mean is 0. As you'll recall, you can give t.test a command, an additional parameter mu equals whatever to test the null hypothesis that the difference is equal to some value. The vast majority of the time, though, when you're using a paired t-test, you want to test the null hypothesis that the difference is equal to 0. If you don't specify a value for the alternative, if you don't specify a value of mu under the alternative hypothesis, it's assumed to be 0, which is what we want in most cases. But in order to do this with t.test, it still requires us to compute this intermediate variable ATP.diff. Just to illustrate the generalizability of the t.test command, or the versatility, I should say, if you didn't want to subtract the one column from the other column, you could do something like this, where you say t.test ATP, comma 1, which is the first column, ATP bracket, comma 2, and then say paired equals true. As you'll see, that gives exactly the same result. That it saves you the trouble of having to calculate this intermediate variable, which isn't that big of a deal, but it saves a couple keystrokes. In general, in R, if you say t.test of x, comma y, and then paired equals true, that will tell R to perform a paired two-sample t-test. The first element of y will be subtracted from the first element of x, the second element of y subtracted from the second element of x, and so on. This only works if you add the parameter paired equals true. If you don't say paired equals true, it will perform an unpaired test by default, and I'll discuss the unpaired test here in a few minutes. And as you'll recall, just basic R notation, if you say x bracket comma 1, that'll give the first column of x, and x bracket 1 comma would give the first row of x. So let's say that we sort our data in a different format, something like this. I put this data set on Sakai as well, ATP2.CSV, and say that the ATP values are all in the first column and the treatment is in the second column. You might do this if you're running a big study and you just have a column that indicates whether they got the active drug or placebo. In this case, pairing the values one to another and subtracting them would be a pain to do the manipulation in either R or Excel. So it turns out that t.test is smart enough to do this for us in this case. If we say t.test ATP twiddle treat, comma paired equals true, then once again we get exactly the same p-value that we got before. It automatically pairs the appropriate element of the pre-treatment group to the appropriate element of the post-treatment group, calculates the differences, and computes the t-test. And if we've seen this notation before, in case you don't remember it, in R, generally speaking, when you see y twiddle x, that's a formula object in R. And you can think of it as saying that we're trying to predict y based on x. In this case, we're trying to predict what the ATP level would be based on whether or not the treatment has been administered. And I'll note here that you need to be careful when using the syntax for paired t-tests, that R will automatically match the first value of y to the first value of x, or the first value of y where x equals 1 to the first value of y where x equals 2. In this case, it will match the first value of ATP where the treatment is pre to the first value of ATP where treatment is post. For this data set, that's what we wanted, but if the data is in a different order between the two groups, then that would cause problems. So be careful with that if you use this notation. So now let's consider the case where the data is not paired, that we want to do a general two-sample t-test. The match pairs two-sample t-test only works if you can match each subject in one group to the subject in another group. But maybe there's no obvious pairing. Maybe the sample sizes aren't even the same. Maybe your control group is much larger than the group which has the disease, which will happen sometimes if you're studying a rare disease. In that case, we need to use a two-sample t-test. A two-sample t-test. The assumptions of a two-sample t-test, you have two distinct populations, and all the observations both within the groups and between the groups are independent of one another. For a paired t-test, the data points within a group are independent, but between groups they're not independent. In the ATP example, we measured the ATP levels in a given mouse pre-treatment, the ATP levels in the same mouse post-treatment, so we don't expect two measures from the same mouse to be independent. But in an unpaired t-test, we're assuming that the observations are all completely independent of one another. So the notation for a two-sample t-test, again, apologies that my bars disappeared and that some of the subscripts got cut off here. We have the first sample and the second sample, or we have the sample size, the sample mean, the population mean, the sample standard deviation, the population standard deviation, that say a treatment group and a control group, it could be any two groups. The sample size of the first group is N1, the sample size of the second group is N2. Likewise, the sample mean of the first group is X1 bar, the sample mean of the second group is X2 bar. Likewise, the population mean of the first group is mu1, population mean of the second group is mu2. You get the idea. It's the same thing for sample standard deviation and population standard deviation. So to find the distribution of the sample differences, we do something similar to what we did in the one sample case, that we use x1 bar minus x2 bar to estimate mu1 minus mu2, and under the null hypothesis, x1 bar minus x2 bar will be normally distributed. Expected value of x1 bar minus x2 bar will be mu1 minus mu2. And the variance of x1 bar minus x2 bar will be sigma 1 squared over n1 plus sigma 2 squared over n2. I'll note in passing, when you do this two-sample test, you'll almost always want to test the null hypothesis that mu1 equals mu2, in which case mu1 minus mu2 will be equal to 0. With two-sample z-statistic, just tossing it out there in case you ever see it, if population 1 is normal with mean mu and standard deviation sigma 1, and population 2 is normal with mean mu2 and standard deviation sigma 2, then the distribution of x1 bar minus x2 bar minus mu1 minus mu2 divided by the square root of sigma 1 squared over n1 plus sigma 2 squared over n2 will be normally distributed with mean 0 and standard deviation 1. This only works if sigma 1 and sigma 2 are known. In general, they will not be. And if sigma 1 and sigma 2 are unknown, then you can calculate a two-sample T-statistic where, again, population 1 is normal with mean mu1 standard deviation sigma 1, population 2 is normal with mean mu2 and standard deviation sigma 2, then x1 bar minus x2 bar minus mu1 minus mu2 divided by the sample standard deviations s1 squared over n1 plus s2 squared over n2. That'll be T distribution, that'll have a T distribution with k degrees of freedom. And in general, it turns out this doesn't exactly have a T distribution, even if the both samples are normally distributed, except in a few strange special cases. In practice, it's close enough that the results will be valid. And the formula for the degrees of freedom is really ugly. I'm not even going to torture you with it. R will calculate it automatically, so just use R and life is good. And also, as I said before, under the null hypothesis, you almost always want to assume that mu1 equals mu2. So an example of a two-sample t-test. We have 30 plants that are randomly assigned to one of three different groups, two treatment groups and a control group, and we want to see if either of these treatments increase or decrease plant growth compared to the control group. I think I used this example in a previous lecture. This data set is built into R. In any event, here's some side-by-side box plots of this data set. With a sample of size 10, we're sort of pushing it in terms of the assumptions of the t-test. It's okay if the data is reasonably well behaved, but if it has major outliers or skewness, it might be dangerous to use the normal distribution with such a small sample size. We look at this data set, we don't see any evidence of major skewness or outliers, so it looks like a t-test is probably okay. So, to do this in R, we can use the t.test command again. Like I said, if you want to try this yourself, the plant growth data set is built into R. So we say t.test weight. This plant growth data set has two columns, one which is weight, which gives the weight of the plant, and one which is group, which either control treatment 1 or treatment 2. So here we say t.test of weight, where the group is equal to control, and we want to compare it to weight where group is equal to treatment 1. And as you can see here, the p-value is 0.25, not statistically significant. Now in general, if you say t.test of x comma y, it'll perform a two-sample t-test to test the null hypothesis that mean of x equals the mean of y. And note that we didn't specify a value of mu, nor did we say paired equals true. If you don't say paired equals true, it assumes that you want an unpaired t-test, which is what we get in this case. If you don't specify a value for mu, it assumes that you want to test the null hypothesis the difference is equal to 0, that is, that mu1 equals mu2. In the vast majority of cases where you do two-sample tests, that's what you want. And the syntax where I said weight, bracket, group, equals, control, that tells R to reference only the elements of weight where group is equal to CTRL, that is, only the controls. If I change control to treatment 1, then it gets me only the observations in treatment 2. So if I compare the other sets of groups to each other, I can do a t-test comparing control to treatment 2. We get a p-value that just barely meets the 0.05 threshold for significance. If I compare treatment 1 to treatment 2, then I see a bigger difference between the two, which is consistent with what we saw in the side-by-side box plots. So when would you want to use a two-sample t-test and when would you want to use a matched pair t-test? If each element of the first sample can be paired to a similar element of the second sample, then the matched pairs design will generally give you better power. But if you do inappropriate matching, you'll lose power or get inaccurate results. It's kind of similar to the concept of blocking in experimental design. For example, let's look at the ATP data. Let's compare the results for the paired test, the unpaired test. In this case, we get a p-value that's smaller when you do the unpaired test. Usually that's not what you expect to happen, but in this case that p-value would be overly optimistic because, like I said, the unpaired t-test assumes that the two groups are independent. In this case they're clearly not because they consist of duplicate measures from the same mouse. So we get a p-value that's overly optimistic because it has an effective sample size that's larger than the real sample size. The paired t-test is more appropriate here. This is similar to the idea of blocking in experimental design. If you can put your data into homogeneous blocks, then you'll get better results than if you just randomize completely. But if you put your data into blocks that are not homogeneous, then bad things happen. Likewise, the paired t-test is better when pairing is appropriate, but if you do the paired t-test in an inappropriate situation, then you'll get lower power and or spurious positive associations. And also note in passing that the format t.test y twiddle x only works if x has exactly 2 levels. We couldn't use this syntax for the plant growth data because group had 3 levels. If it only had 2 levels, control and treatment, we could have done that and saved ourselves some typing and not have to use the brackets and group equals equals control, whatever. But we have 3 levels, so that wasn't an option. So when designing experiments to do a two-sample t-test, you'll get the best power if the two groups have approximately equal size. That, in general, the power of your test is determined by whichever group is smaller, cases or controls or whatever the case may be. So you'll get the best power if the control group and the case group have approximately equal sizes, ideally exactly equal sizes. That's not always possible, and it's not the end of the world if they're not exactly equal, but if you can only collect a fixed number of samples, you'll get the best power if you collect the same number in both groups. I'll note in passing that you can do an equal variance two-sample t-test in R. You can say t.test x, y, var.equal equals true. And it can possibly increase your power a little bit if you know for certain that the variances of the two groups are equal. In practice, you can almost never be certain of that, and even if they are equal, it doesn't give you that much power in the first place. So my recommendation would be to just not bother with it, but I'll mention that in passing in case you ever need to do it. It's not something I'm ever going to ask you to do in this class. I'll also mention the association between confidence intervals and two-sample t-tests. When you perform a two-sample t-test, you can also construct confidence intervals for the difference between the two means. It's exactly the same procedure as in the one-sample case. I'm not going to go into the details on this. I recommend that you just let t.test and R calculate it for you automatically. But when you write papers or when you write a final report for this class, hypothetically, you should report confidence intervals along with your hypothesis tests because, in my opinion, the confidence intervals are almost always more informative. So, also mention the usual caveats about hypothesis tests. Both samples have to be representative samples from the population of interest. If you have a biased sample, then you're going to get incorrect results no matter what you do. The observations must be independent of one another and independent of the observations in the other group. with the exception of the paired two-sample t-test. If you compare one sample to another, then the two observations in a pair you do not expect to be independent. And the two populations also need to be normally distributed if the sample size is small. In particular, if there's bad outliers, that can cause problems. Important things to remember from today's lecture: you use two-sample t-test to test the null hypothesis that the means of two samples are equal to one another. The matched pairs test works well if each subject in group 1 can be matched to a subject in group 2. If you can't perform any sort of logical matching, which is true in most cases, you're better off using the unpaired t-test. You want to make sure that the tests of your sample make sure the assumptions of your test are satisfied, that your sample is representative of the population, that the observations are independent, and at least approximately normally distributed for small sample sizes. And you should also report confidence intervals for the differences between means. In our t-dot test of xy performs a two-sample t-test to perform the null hypothesis that x and y have equal means. If you add paired equals true, then it'll perform a matched pairs test, and you can use the syntax t-dot test of y twiddle x if x is a factor with exactly two levels. And if you want to reference only the controls in x, you can say x bracket y equals controls, or whatever the case may be. If you go x bracket comma 1, that'll give you the first column or the first row or things like that.